Good morning, students. Today we are going to discuss Born approximation and its validity. It was introduced by Max Born. Max Born was a German physicist. He was a Jew. In fact, we know that the wave function which was introduced by Schrödinger, which is nothing but psi, in the year 1926. But psi must be a real number. As far as we are concerned, we know that any quantum mechanical particle should be real. But psi is a wave function. This can be a complex number also. So psi can be a real number or real part as well complex part. So if it is a complex part, it means that it is an imaginary number which can't be realized. So psi alone has no meaning at all. It must be a real number. For any classical object, if we want to measure any reading, it must be a real number. Whereas psi is a complex number. So just to take the complex conjugate of any psi, multiply with psi, that will give us a real number. So which is nothing but mod psi squared. Which is nothing but mod psi squared. Now psi squared has a real meaning. Psi is a complex number. We are going to multiply with its own complex conjugate, then this will become a real number. Then real number can be observed. So we can understand that any quantum mechanical system which is represented by mod psi squared, then that can be understood. So which was introduced by Max Born. So very famous Max Born. He introduced in the year 1926 about psi squared. In fact, he got the Nobel Prize only in the year 1954 for the statistical interpretation of probability of density. So in the year 1954 only he got the Nobel Prize. Max Born, Heisenberg and Jordan, three introduced matrix mechanics. So we already studied matrix mechanics earlier in quantum mechanics 1, and the main part was given by Heisenberg. We know already, Werner Heisenberg. But all the three, Max Born, Jordan and Heisenberg, all the three only discussed about the matrix mechanics, which is very important in quantum mechanics. And subsequent years, after 1926, Albert Einstein nominated them, all the three, for the Nobel Prize, but they did not get it. Together they did not get it. But Werner Heisenberg alone, he got the Nobel Prize in the 1932. So he got the Nobel Prize 1933. So he was nominated as a Nobel laureate in the year 1932, and he got the Nobel Prize in the year 1933 along with Erwin Schrödinger and Paul Dirac. In fact, Max Born, he came to India in the year 1935. He stayed here for 2 years in IIC Bangalore. So you know that in the year 1933, as he said that he was a Jew, 1933, Hitler came into regime. So at the time all the Jews were expelled. So first he went to England and stayed for 2 years. After that he came to India. He stayed here in IIC Bangalore, and he could not continue. He stayed here for 2 years. He could not continue because he was not given a good position or a permanent chair at IIC Bangalore. At the time Professor C.V. Raman was there, he was the director. So again he went back. So famous scientist Max Born. Max Born is not only famous for Born approximation or Born series, but also for many things. Born equation, Born squares, Born coordinates, Born Oppenheimer approximation is very famous for all those things. So in this class we are going to discuss what is this one? Scattering amplitude. So yesterday we discussed about scattering amplitude. So this is a scattering factor, and we are going to derive the equation using Born approximation. And our aim is to find out the wave function. Okay, first thing is we are going to find out the wave function using Schrödinger's time independent equation. First point. Second point is, we are going to assume the weak potential. The potential is very, very weak. If potential is very, very weak, we know that the total energy equals kinetic energy plus potential energy. We know already. So just now I said that potential energy term, which is connected with the potential term, interaction potential, it is very, very weak. If it is very, very weak, it is small quantity. So kinetic energy must be larger. So this is the idea. So if potential is very weak, kinetic energy of the incident particles must be very large. So very important one more question. Born approximation is valid only for weak potentials. Okay. Then, as we discussed in the last class that about Helmholtz equation. Can you remember Helmholtz equation? The solution of Helmholtz equation is Green function. So here also we are going to have the Green function. We are going to get the solution, and this solution will be compared with yesterday's discussion. Yesterday we discussed about the relation between scattering amplitude and differential cross section. So we had one complete wave function, which is a linear combination of plane wave equation and spherical wave equation, correct? So this is the idea. We are going to get the solution using Green function. This solution will be compared with that solution yesterday we discussed, and we are going to obtain scattering amplitude. That's all. Suppose if scattering amplitude is known, square of the scattering amplitude will give us differential cross section, which is experimentally observed value. So we are going to compare. So that's the idea. Okay. So we know that K and K naught, and K naught is the wave vector of the incident particle, and K is the wave vector of the scattered particle. We know already. So this is about scattering amplitude, and square of the scattering amplitude will give us differential cross section. Okay. Our aim is to find out scattering amplitude. Okay. So Born approximation to derive the scattering amplitude F, which depends on theta and phi. Theta is the polar angle, phi is the azimuthal angle, and differential cross section d sigma by d omega using Green function. Okay. So we are going to have Green function. The solution of Schrödinger equation is nothing but a Green function here. So Born approximation is used to evaluate the scattering amplitude, and of course we are going to consider the weak potential. So if the scattering takes place from the scattering centers which are localized, so target is localized, it is fixed, but are weak such that the scattering does not take place at larger distances from the scatterer, and the scattered wave is weak in amplitude. So scattering wave is weak in amplitude, and of course potential energy is considered as a perturbation. So we already studied about perturbation, and we are going to consider only first order perturbation. So we are going to use first order perturbation theory. Hence the Born approximation is the best one in which the kinetic energy of the colliding particle, as I said, weak potential. Potential energy is very, very low. So kinetic energy must be very large. So this is the idea. So our aim is to show the differential cross section at the center of mass frame obtained by asymptotic form. So as I said, scattering problem is a two-body problem. Okay, so that's why M is replaced by mu to make it into one body problem. So mu. So we are going to use Schrödinger time independent wave equation, which is given by equation 6.37. So we have a kinetic energy, potential energy, which acts on the wave function, which will give us the energy and your wave function. So this is a eigenvalue equation we know already. And mu is a reduced mass. Expression for mu will be m1 m2 by m1 plus m2. Okay. Now just multiply this equation by minus 2 mu by h bar square. We will have this equation. Okay, very simple one. So multiply this by minus 2 mu by h bar square, you will get this equation. Okay, very simple one. Now you just replace with k square. So k square equals 2 mu, yeah, this is correct, 2 mu e by h bar square. So as it is like this, you have del square 2 mu by h bar squared v of r. Okay, acts on psi of r will give you, this is replaced by k squared, so minus k square psi of r. Okay, now you just bring that term here. Okay, bring this term alone here and this term to right hand side. Is it okay? You have del square you bring this term minus k squared psi of r here and this term to right hand side. So you will get this equation. And of course V of r is the potential energy. Together this term is called as the interaction energy. Together. Okay. 2 mu by h bar square V of r psi of r, together this term is known as interaction energy. Okay, interaction energy. If potential is weak means interaction energy also will be very weak. Okay. And del squared k squared psi of r. So we know this equation very well, and suppose if right hand side is equal to 0, we can say that this is Poisson equation. If it is not equal to 0, we can say that this is Helmholtz equation. If it is so Helmholtz equation, we can solve using Green's function, so which we already studied in mathematical physics itself. Okay. Then another thing is the general solution to the homogeneous equation. Of course, this is homogeneous equation. If it is equal to 0, this is a homogeneous equation. Not equal to 0, inhomogeneous equation. Okay. So del squared k squared psi homogeneous equation, which is equal to 0. And of course, using this condition, r tends to infinity, V of r equal to 0. Yesterday we discussed. Your V of r will be minus e squared by 4 pi epsilon naught r. Okay, we know already this. So when r tends to 0, your V of r will be 0. If V of r equal to 0, this term will become 0. And of course, this is your homogeneous equation. Okay. So del squared k squared psi homogeneous of r equal to 0. This is very, very important equation. Often we'll be using. Just remember this equation. Okay. The solution of this equation, it's nothing but a plane wave equation. Yesterday itself we discussed. Okay. It's a plane wave equation. Okay. Psi incident is nothing but a plane wave equation. And of course, yesterday we replaced k by k naught. Okay. Now you remember this is, let it be k will for the time being. So the solution of this equation 6.41 will give us plane wave equation. Okay, is it okay? Okay. A particular solution can be expressed in terms of Green function with an interaction potential. Now we are going to add interaction potential. So when interaction potential is added, we are going to solve the solution. We are going to solve the solution, and if it is so, the solution will be Green's function. So okay, that's the idea. I repeat. If it is equal to 0, it is a plane wave equation. If it is not equal to 0, this equation, correct? So this equation, the solution of this equation is nothing but Green's function. The inhomogeneous Helmholtz equation, which is not equal to 0, right hand side. Okay, inhomogeneous Helmholtz equation is solved by Green's function. Of course, this is where Green's function, g of r comma r prime. For any Green's function, we need to have at least minimum 2 coordinates. So we know already r and r prime. Here also we have 2 coordinates. As I said, this is 2 body problem. Okay, 2 body problem. So there will be 2 coordinates. Surely there will be two coordinates. So we have 2 coordinates. So Green function be the solution of inhomogeneous equation with a delta function source. I will explain little bit later. A delta function source. Of course, delta function source is a point source. Delta function also is minimum. There will be 2 variables, r and r prime. Suppose if r and r prime both are equal, the answer will be 1. If r is not equal to r prime, answer elsewhere it will be 0. So we know already about a delta function. Hence the Green function is obtained by solving point source equation. So both are equal. We are going to prove this one in terms of Fourier transform. We are going to prove. The function g of r and r prime is called a Green function, and itself satisfies the differential equation. So it should satisfy the differential equation. Okay, and of course we are going to replace, instead of psi of r, we are going to replace Green's function here. Okay, so del squared k squared acts on Green function is nothing but your delta function. What does it mean? This happens only by means of Fourier transform. I repeat, just take Fourier integral of Green function. Okay, it will be in k space. So when it is a real space, R space, you are going to take the Fourier transform, it will be in k space. Okay, momentum space. Suppose we are going to take the Fourier integral of k space, it will be in R space, position space, reciprocal lattice. Okay, so this is what we discussed earlier, we know already. Now take the Fourier integral of this Green function. It will be in reciprocal lattice, it will be in k space, you will get one expression, correct? Similarly, you just take the Fourier integral of delta function, it will be in reciprocal lattice, you will get the expression. This expression is exactly same as that of the expression which we have obtained for Green function. So that's why both are equal. Is it okay? I repeat, the Fourier transform of Green function which is obtained left hand side will be exactly equivalent to the Fourier transform of delta function obtained on right hand side. So both are equal. That's why we are equating these two. See, look at the previous one. See, Green function, delta function. Okay. So this is the equation. So it provides a useful procedure. So we are going to use this one for determining psi of r. Our aim is to find out wave function. Okay, total wave function. And thereby we are going to get the scattering amplitude. So that's the idea. Okay. It provides a useful procedure which is nothing but a Born approximation for determining psi of r. This can be achieved in iteration procedure known as Born approximation. This iteration procedure probably you would have studied in numerical methods, correct? Iteration procedure. We will have number of series solution will be there. For example, take zero solution. We have one solution. Okay, go for the first order solution. For the first order solution, we will be using the zeroth order solution. For the second order solution, we will be using first order solution. For the third order solution, we will be using second order solution. So the procedure is going on until the input and output should be equal. At the end, we will have some solution. At the end, after using all iteration procedure, at the end we will get the solution in such a way that left hand side will be equal to right hand side. That is, input is equal to output. That's called iteration procedure. Is it okay? Probably you would have studied numerical methods very well. So now what are the properties of Green function? There are mainly two properties which you are going to use in solving the wave function. One is this one. So by setting r dash equal to 0, which determines the solution for the equation. Okay. One is r prime equal to 0 means it's a purely delta function. So if it is so, this equation, the solution of this equation will be always in terms of spherical symmetry of differential equation. So this will have, suppose if r dash equal to 0, it represents a spherical symmetry. If it is a spherical symmetry, we will have to use only spherical polar coordinates. So we will be using later, using this condition, we will be using spherical polar coordinates to solve the problem. So this is one property. I repeat, if r dash equal to 0, it implies that this equation 6.44, this equation represents the spherical symmetry of the differential equation. If it is so, we will have to use only spherical polar coordinates. Okay, so just remember this property, one property. Then another property is translation symmetry. Probably we studied about chronic penny model. Can you remember chronic penny model in quantum mechanics 1? So it's a about periodicity. Periodicity, the condition for periodicity is given by r equals r plus a. A is a periodicity, which we have already learnt earlier in chronic penny model. So this is called a translation symmetry. If translation symmetry, then Green's function depends on the difference between the vector r and r prime, which is nothing but given by this. So your r comma r prime is given by r minus r prime, which is known as relative distance. Okay, so this is known as relative distance. As I said, there will be minimum 2 coordinates. Okay, for this problem there will be minimum 2 coordinates because this is a 2-body problem. So there must be a relative distance between these two particles. Is it okay? So your r comma r prime is replaced by r minus r prime, which is known as relative distance. So now coming to this, we are going to have a solution, and of course this is inhomogeneous equation which we learned correct in 6.40. Equation 6.40 is given by this. Now Born has assumed this equation for the total wave function. Born has assumed this wave function. Okay, and he says that this is the formal solution, and look at the equation. This is your psi of r, right hand side also psi of r, and right hand side also your psi of r. So right hand side and left hand side both consist of psi of r. So which is not the proper solution. Solution means you have psi of r, right hand side there should not be psi of r, correct? So it's a formal solution, but he has assumed that this can be a solution. And what we are going to do is, we are going to insert the solution here in the equation, Helmholtz equation. And we are going to check whether right hand side is equal to left hand side or not. If it is so, if both are equal, then the assumed solution is correct. I repeat, see, Born has assumed this integral solution. Okay, this is integral. Okay, integral solution. And we know already this Helmholtz equation. Just now we learnt about Helmholtz equation. And we are going to apply this equation here, so that if right hand side is equal to left hand side, then the assumed solution must be correct. Okay, so this is what he assumed. So this is the formal solution, as I said, because both consist of right hand side, left hand side consist of psi of r. So this is not the correct solution. It is just the integral form of a differential equation. Now we are going to substitute. We are going to substitute here in equation 6.40. Okay, I repeat. So he has assumed, and we are going to insert this one, and we are going to check whether left hand side is equal to right hand side or not. So that's the idea. So now just take 6.40 equation, del square plus k square psi of r. Okay, which is equal to del square plus k square. What is psi of r? Psi naught of r plus this one. You remember this equation? Can you remember this one? Last class we discussed about the total wave function, which is equal to incident wave function plus scattered wave function. This is exactly resembles with. Okay, you just remember this one. Okay, total wave function. So for the timing we will come here. So del square plus k square, your psi naught of r plus this 2 mu by h bar square integration green function, the same. I have written same function. You multiply now. We can multiply. So multiplying on this first term, that will give us this term. Multiplying with the second term, that will give us second term. Okay, and of course you have d cube r prime is there. That's why we have brought del square plus k square inside the integral. Okay, because del square is d squared by partial d squared by dr squared. So that's why we kept del square plus k square inside. And of course del square plus k squared psi naught of r, equation 6.41 for any homogeneous equation, that's equal to 0. So this term will become 0. The answer for this term will be 0. And this term exactly I have written exactly like this. Is it okay? Is it okay? 6.48. So now we know that del square plus k, I have written the same thing. Instead of g, r minus r prime can be replaced by your del cube r minus r prime. Okay, so now replace with g, green function with the delta function. So green function with the delta function. When r equals r prime, when r becomes r prime, delta function answer will be 1. So we know already. Okay, elsewhere it is 0. So when r equals r prime, your integral delta function, that will be equal to 1. The remaining factor will be 2 mu by h bar square. Your v of r equals r prime. So v of r, psi of r. What is this one? This is exactly right hand side equation of the earlier one. Correct? See, right hand side of equation. I repeat, this is what he has assumed. Okay, and we are going to insert this equation, and we are going to check whether the right hand side is equal to left hand side or not. So we have inserted now. See, look at this one. Exactly it is equal to this. So the assumed solution is correct. Okay, so this is what this idea. So which is the right hand side of equation 6.40. This is equation 6.40. So the assumed solution for the problem is correct. So equation 6.46 is correct. So equation 6.46 is correct. That is, integral form of the green function is correct. So this is what he has assumed. So this is known as the integral form of Schrödinger equation, and it is given by, and it is given by this equation. So you have psi of r, which is equal to, I have replaced the psi naught with psi incident of r, psi incident. So incident particle energy, the wave function. So psi of r plus 2 mu by h bar squared, the remaining terms. Is it okay? You just compare with the equation which we studied in the last video lecture. So psi of r equals psi incident of r plus psi scattered of. The linear combination, as I said, superposition of incident wave and scattered wave. You can compare this one. Okay. So your psi scattered you just compare with this one. That will give you, this will be your psi incident and this must be your psi scattered. See, you compare these two equations. You have psi of r, this will be psi incident of r, and this term must be equal to psi scattered. So this is your psi scattered. So it provides a useful procedure which is nothing but Born approximation. We are going to determine your psi of r. Again, look at the equation. This it contains psi. This also contains psi. So this is not a formal solution. So this is not an exact solution because both the terms, right hand side, left hand side, contain psi. So which is not the correct solution. Okay, this is not the correct solution. Now we have again we have two properties for green function. Suppose if it is r prime equal to 0, then this can be replaced with minus e power I k r by 4 pi r. So we already studied green function properties earlier in mathematical physics. They are exactly same expression. If it is so for the relative distance, then this must be minus e power I k modulus r minus r prime divided by 4 pi r minus r prime. This r is extra I have written. Okay, that's wrong. 4 pi r minus r prime. Okay, is it okay? Now instead of g r minus r prime, we are going to replace. Just to replace. Okay, just to replace. So this is your incident. This is psi incident. Psi incident can be replaced by plane wave equation. A e power I k naught r. See now k naught r. It's a plane wave equation. Now here it is plus. Here it is minus. So that's why you written as minus. Okay. These two and these two will get cancelled. So you will get 1, 2. So we have 2 pi. Is it okay? These two and these two will get cancelled. You have 2. So remaining pi will be there. So mu divided by 2 pi h bar squared integration of all these terms. Is it okay? Again I repeat, psi of r, here also you have psi of r. It is not the exact solution. Okay, so this is not the solution of wave function because the wave function is inside the wave function. The wave function which contains again the wave function inside. So this is not the correct solution. Generally the range r prime integral is limited by the range of potential energy V of r to a microscopic distance. Of course, we learnt already about this. This is just an integral equation. This is not an unknown solution of psi of r, as just now I said. We have rewritten Schrödinger wave equation in the integral form, which is suitable for scattering theory. So equation 6.54 is solved approximately by means of a series of successive or iteration procedure, which is nothing but your Born series. So this is equation 6.54. So 6.5. Now we are going to solve in terms of series. Okay, series of solution, because you consider first for a particle, one particle. So one particle collides with the other particle. The other particle will collide with another particle. Another particle also will collide with successively. The collision will take successfully. So that's why it's the first series, second series. That's why it's termed as Born series. Okay. Now we'll go for the zeroth order, the first collision. Okay, zeroth order. For the zeroth order, this is the equation. Okay, this is the general equation. See, this is this equation 6.54. And we are going to consider, the first point we are going to consider is potential is very weak. The first approximation for Born approximation is potential is very weak. So potential is very weak. It's very low. So we can say that potential energy is almost equal to 0. So your incident wave psi naught of r equals a e power I k naught r. So your psi naught of r will be your incident wave function. The first one. So which we call this as the zeroth order solution, and the above equation is zero order wave function. So first one we have finished. First one is nothing but the incident wave function, which is nothing but zeroth order solution. Okay. So this is your zeroth order solution, which is nothing but the incident wave function, which is equal to a e power I k naught r. Now we will go for iteration procedure to go for the first order, second order, third order, goes on.